And let me go back to this. Okay. But the problem set's due tomorrow evening, I think. And like I said, I'll try to post stuff over the break about the midterm, you know. But I think I've told you all it'll be like Friday after break, will be the sit down. I'll give you some time, like you'll have a period where you can sit down and take it. No books, no notes, but you can use a cheat sheet, like a front and back piece of paper. You can write whatever you want on. And then you'll upload your sort of first attempt solutions in your cheat sheet. And then you'll have a week after that to write up really nice solutions. Yeah. I'll probably give you like, I think on Gradescope, I can give you a time limit from when you access the file to like, so I'll probably give you like, let's say 4 hours just to like, so you have a couple hours to take it, but then also you can upload it and scan it and upload it and all that just to make sure you have enough time. What I'm gonna do is on Fridays, I actually have a lab period for my other class that I don't really use. I just use it as like an office hour kind of thing. And I'm gonna be available then, and I'll post that. It's like 11:30 to 1. So if you wanna come in and take it in front of me, you can, in case you have questions. But you can also just take it like I'll give you like a 36-hour window or something when you can take it, so you can find a good time for you. But if you wanted to come take it in front of me, you're welcome to. So you can come ask me questions and stuff. So, but if you want to just take it at home, you can do that too. Yeah. Next Friday. Yeah, not 48 hours now. Maybe that's what the student thought. Maybe he thought the first pass of the test was today or something in class, maybe. So, yeah, next Friday, and then you'll have a week after that. Yeah, so you'll have time to prepare. Yeah, there's just some positive benefit to actually studying for a test. If I just gave you a take home that you could just start looking at and go look at the book and stuff, there's benefits to that too, but I think there's some benefit also like forcing yourself to try to recap everything and sort of, what's the word? I don't know, crystallize all the concepts and stuff before you sit down and take the test. So anyways, so that's that. And again, I'll post more details and instructions about that. But I did want to today, I want to finish up, I want to get into the multivariable chain rule, but I also just wanted to finish up a few things about the directional derivative, especially conceptually, because I meant to sort of, I think class Monday, Friday and Monday were much more about the gradient, right? The 2D gradient and the 3D gradient. And I sort of haven't talked about the directional derivative since maybe like last Wednesday. So let me just first remind you that there's like, a couple different ways to conceptualize the directional derivative and write down the directional derivative. And they also work in both 2 and 3D, and really any dimension. Directional derivative. Right, so for a function z equals f of x comma y, or w equals f of x comma y comma z. So here the gradient of f is partial x comma partial y, and here the gradient of f is a 3-dimensional vector, right? Partial x, partial y, partial z. At a point P, which would either be a 2-dimensional point in this case or a 3-dimensional point in that case, the directional derivative in the direction u, because now we're like basically on a surface, or well, in space at some point where we have some function and we're at some specific point and we want to know the rate of change if we go in a specific direction. The direction u, and u is a unit vector. is, remember, so we write it this way. I said FU, it's fun to say FU. And it's the gradient at P. That's a specific vector, right? Because we plug in a specific point and we dot that. We take the dot product of that and U. But so that's one way to do it. So if you have a specific function at a specific point and a specific direction, you can just write down the vectors and actually just plug into this formula, right? But the other thing I wanted to mention is that we said also before that if we use the geometric definition of the dot product, right, that it's the magnitude of this vector times the magnitude of this vector times the cosine of the angle between them. And that's a unit vector. So we end up just getting this other formula, which sometimes is useful. Cosine theta, where theta is the angle between the gradient of f at P and U, right? And so just in different contexts, this is more useful. Like on the problem set, I saw students going back and forth. Like this is, if you know the angle, if you know the direction of max increase, remember the gradient's the direction of maximal increase, right? So if you know the direction of maximal increase and you know that you're going away from that in a certain angle, then you can use this formula to find the directional derivative. Does that make sense? So you can use either formula depending on what information you have. And so that's sort of, I just think, a useful thing to keep both of those in mind. It's almost like when we did the geometric definition, just the two definitions of the dot product, right? One was the sort of just multiply like components and add, but the other was multiply the magnitudes and times the cosine of the angle between them. And just depending on what information you had, you could use one or the other. So, okay. And, well, actually, this might be more relevant for the next, the other image I wanted to show, but I guess also I should just say this is the rate of change. This is the rate of change of F, right? This thing is really the rate of change of F. The instantaneous rate of change of F. Rate of change of F at P in the direction U, right? So just, you know, this conceptually, there's a conceptual sense of what the directional derivative is. There's sort of a more algebraic formula and a more geometric formula. And it's just trying to keep all three of those aligned in your head and straight and know which one to use in which situation. So maybe thinking about the conceptual definition, this is something I just took straight from the book. And I like talking about this because, well, let me not give it away. Oh, let me share screen. Okay, so here's an example. And I think there's a problem on the homework that's similar about like deciding whether directional derivatives are positive, negative, or zero. And here it says, yeah, you're given like a contour map at the indicated point in the indicated direction. I guess there's specific vectors here. V is I plus 2j, W is 2I plus j. Try to decide whether the directional derivative is positive, negative, or zero. And I think these are all instructive because there's some subtleties here. I've sort of said, when we talked about the sign of the partials, I sort of said just whether you're going towards a higher or lower contour. That's kind of what you're just looking at. And so there's some things that are obvious, like W here. It's pretty obvious that you're starting on the 4 contour and heading towards the 5 contour, so that's a positive directional derivative, right? Using the mouse to gesture. Yeah, here, this is, so this directional derivative is positive, right? Let me come back to V and the V direction for this here. Here, you might think it's a little more subtle because you kind of leave the 6 contour, but it's almost like you're not heading towards the 7 contour, you're heading again to like the 6 contour over here. But I think the thing to keep in mind is that This is an instantaneous rate of change. It's like what's happening just at P. And as soon as you leave this point, like if I'm just a hair off of this 6 contour, what kind of value would I have? Yeah, it could be like 6.01. There is like a 6.01 contour that's not drawn in this picture, right? And a 6.02 and a 6.03. There's like 100 contours you could draw between 6 and 7. There's a million contours you could draw. It depends on however you just want to draw your contour. I mean, however many contours you want to draw, right? And so I think it's worth just thinking, okay, as soon as I leave this contour, I'm actually I'm a little bit bigger than 6 right here, right? You see the mouse. So that's going to be a positive directional derivative also. Whereas if I leave the contour going this way, I'm between 5 and 6. So it's a little less than, as soon as I'm off this contour, the value of the function is a little less than 6. So that's going to be a negative rate of change. Does that make sense? Even though it's not pointing right at the next contour, it's still like the region between contours is just, we can assume, I think it's fair to assume that if we're between 2 contours that we're not, there could be a contour between these two, 6 and 7, that's like 5.5. So it's actually going down and then going up. But we don't have that much information, right? We just can go with the information we have. So, and if there was a 5.5 contour, then there actually should be another 6 contour because we'd have to get back up to 7. So like you'd almost need more, there'd be more to the 6 contour. So like, I think it's fair to assume that. There is some assumption there. Going back to the V over here, it's a little hard because it's not exactly clear. But if you zoom, like it looks like you might leave the contour and be a little bit bigger than 4, if you go in the V direction. But the more you zoom in on this, what's going to happen to the contour the more you zoom in on the picture? It's going to straighten out into straight lines, right? And so if you zoom in enough on this, the V is really pretty much following the contour, right? And if you're following the contour, what's happening to the values of F? Staying the same. It's not going up or down. So here, I would say that the directional derivative is 0 in this direction because you're actually going in the direction of the contour. I'd feel a little better if this was tangent, like a little more obviously tangent. And that's the thing to worry about too, is that if you're tangent to the contour, the arrow might actually stick into this region between 3 and 4. If this is more perfectly tangent, or the curve was more obvious where you could really tell it was tangent. But the tangent line is usually on like the side of a curve, right? So then it looks like maybe you're going into the bigger region. But you have to think about when you zoom in, the tangent and the curve would become identical because you zoom in and these things straighten out, right? So if you're tangent to a curve, then it's like, yeah, I guess I could draw it probably more, maybe even more extremely. Let me try to draw this even like with more. So directional derivatives on contour maps. Let me try to draw. So say we had just something like, we have some contour that's like that, and this is like labeled 5, and the next contour is like that, and it's labeled 6, and this one is labeled 4. I guess what I'm saying is like, if we pick this as like our U1 direction, this is our U2 direction, and this as our U3 direction, right? So the the directional derivative in U1 is positive. The directional derivative in the U2 direction, which is that one, is negative. But I would actually probably say the third one, that this feels like it's tangent to the curve. And so if you zoomed in more and more, you would actually see these going in the same direction. So you really would be following the contour. Just, this is a very long vector. Really, you should think of zooming in for 100 years at a rate of 10 times magnification per second. That's a lot of zooming. Maybe if we were immortal beings, we would do stuff like that because we get bored. Hey, let's zoom in on this graph for 100 years in a row. That sounds like a fun way to kill another 100 years. We're gonna be around for eternity. Never mind. All right. So to me, like, because this is tangent to this contour, I would actually claim that this is 0, or maybe approximately 0, because U3 is tangent. So even though it looks like it's leaving the 5 contour and heading towards the 4 contour, you got to think about the fact that it's actually tangent. I mean, I'll try to, anything I give you to the contour, anything I give you, I'll try to make it kind of obvious what I'm expecting. Okay. Any questions about that? Now, the third picture is actually even weirder. Because the book, I keep meaning to write the authors of the book, because now we're in the 8th edition of the book, and this has been wrong in like 3 editions. They say that both of these directional derivatives are negative. That seems very plausible, right? Because you leave the 10 contour and you head towards the 9 contour. But what's different about this? This 10 is like a peak, right? It's 9 on both sides. And so either way you head off the contour, you're going down. Think about what that means, like when we have a function of one variable, right? If I tell you, you go left, you go down, you go right, you go down, what kind of point are you at? A local max. What's the derivative of the local max? 0. So in fact, if you're at a peak on a curve, on a surface, it's the same thing. Like, just what the tangent plane would look like at this point. The tangent plane at all of these points would be horizontal, if that's really the top. It's like the top of a ridge or something. The tangent plane would be horizontal. We're going to talk about this actually. That's actually the next thing we're going to do after the chain rule, is like optimization and finding peaks and valleys and local maxes and mins and stuff. But you can kind of guess that what you want is you want both partials to be 0, or you want any directional derivative to be 0. So in this example, actually, I think that these directional derivatives are both 0. But the book says they're both negative. And I keep thinking they're going to change it from one edition to another. And they keep doing the same thing. So maybe I should finally write them and tell them. Yeah. But so do you see that? Like, it's actually probably, because you're at the top of a peak at that point, that it almost should be that the directional derivative is 0 in any direction. Yeah. That's right, at a minimum 2. If you're at a point that's a local max or a local min, and as long as it's smooth, then, I mean, otherwise the directional derivatives won't be undefined or something. But yeah, so those are actually both, I think those should both be 0. But if you look at the book at this section, it says they're both negative. So, okay, so that was one thing conceptually I wanted to bring up. The other thing was I usually assign this problem right here. I assign 99 from this section. I often assign this problem. Part of the reason I didn't is because I'm going out of town today and you're not going to have a chance to talk to me, because about half the class would come in and ask me about this problem. So I thought maybe we'll just do it together because it'd be fun. So you're climbing a mountain by the steepest route at a slope of 20 degrees. So that's up 20 degree, like 20-degree ascent slope, right? When you come upon a trail branching off at a 30-degree angle from yours, what is the angle of ascent of the branch trail? This looks like a fun problem, right? Are you sad I didn't just assign it on the homework and make you think about it for a couple days? Yeah, so I want to write on the board. So let me stop the share and actually write some of this on the board. So I think this is, what is it, 14.4, number 98. So climbing mountain, in direction of steepest ascent. Because we're used to, when we think about going up mountains or roads and stuff like that, we actually usually often give this ascent, the rate in an angle, right? Like the gradient on roads and stuff. 20 degrees is the rate of is the steepest descent angle. So already, first off, like before we even look at the rest of the question, it's sort of like, what can you glean from this? There's something about the gradient involved here, right? We're going in the direction of the gradient. And so i.e., we're going in the direction of the gradient. Now, we're not actually given any specific universal directions, or it doesn't tell us we're going northwest or southeast or anything like that. So everything's going to be relative, right, to this direction. So we don't know the actual direction of the gradient vector, but I claim we can figure out the magnitude of the gradient from this. Yeah, how can you figure out the magnitude of the gradient? Yeah, well, it's like, what is the 20 degrees? Well, so the gradient, so that's for the directional derivative. Right, so that's the funny thing is there's two angles in this problem, 20 degrees and 30 degrees. It's like, what do they each mean in this question? So, can anybody see what is it like? If I tell you you're going up at a 20-degree angle from the horizontal, how can you figure out? If you're going up at a 45-degree angle, what's your slope? 1, right? So you know for 45-degree angle, the slope's 1. This is a 20-degree angle. So actually, I think it's worth drawing like the side view of this problem. So we basically have something like this. Also, I'm guessing we're kind of assuming the mountain's a ramp at this point. Like it's like zoomed in enough that we're just thinking about it being just like a ramp that we're on, right? So the side view is like we're here and we're going up this route right here. And we know that this angle is 20 degrees. Right? If I know it's 20 degrees, how do I find the slope from the angle? Tangent, right? Opposite over adjacent is perfect here. It's rise over run. So tan 20 degrees equals opposite over adjacent, which equals rise over run, which equals slope. So the tangent of 20 degrees is the slope there. If we do it, I'm just gonna ask Google real fast. So it says the slope is 0.364. That's good, it's less than 1. That makes sense, right? 20 degrees. So this is about 0.364. So this is actually the magnitude of the gradient here, because it's the rate of steepest ascent, i.e., magnitude of the gradient is tangent 20 here. It's about 0.364. So that's the information we can glean. We can't really get gradients of vector. We really should want a direction and a magnitude. But since this is sort of, we're not really told anything about direction specifically, best we can do is get the magnitude of the gradient. Does that make sense? Okay, so that was the first part of the question. we sort of gleaned all this information from. The went to the wrong browser tab, didn't I? Okay, just putting the question mark on the screen. So the second says, oh, we come upon a trail branching at a 30-degree angle from yours. What is the angle of ascent of the branch trail? Sorry? Yeah, but the theta where? Here? The FU. Hey, don't say FU to me. Disrespectful? No, just kidding. No, yeah, so right, so now it's like, so then, yeah, branch trail. I mean, this is a highly idealized mountain that's somehow become just a ramp. Yeah, right. This is all like, this is all in the instantaneous, and we're just kind of assuming that like the trail we're on is straight, and then the branch trail is straight for a little, just to like, I don't know if you're actually hiking, if you'll ever think about stuff like this. You should try it, see if it helps. I don't know, okay. So branch trail at a 30-degree angle, from the steepest descent trail. So that means, right, so this is a side view. This is actually gonna come up, I think, when we're doing things like triple integrals and stuff. That'll be fun. And just in 3D, sometimes it's nice to draw, since we can't really see the whole object ourselves sometimes, it's nice to draw like a side view and a top view, because you can't really draw the whole 3D picture, unless you're a better artist than I am. So side view is this, but what I want to say is now we can actually draw a top view. If we draw a top view, we're going to see the 30 degrees. So the 20 degrees is sort of like from the horizontal, like from the horizontal going up. But the 30 degrees is like, that is a like horizontal change in direction. Yeah, I love this problem because it really, the two angles there just really can throw people off because they're used in totally different ways in the problem. So now we can draw a top view of this picture. And whatever my direction of, the main trail, steepest ascent, whatever direction that is, looking straight down from the top, now we're going off at some 30-degree angle. That's kind of a little bit horizontal. Right, but it's just important to think that this is a top view, not a side view. This is looking down from above. And this is the branch trail. And then we can really use the rate of, like if we want the rate of ascent of the branch trail, that's the directional derivative in that direction, right? So rate of ascent of the branch trail equals the directional derivative in this direction. But again, we don't have sort of like universal directions. So we don't really have the vector that gives us the u. We don't have the u vector. But here we can use the magnitude of the gradient, what I just erased on this board, I think, times the cosine of the angle between. Right. And so here that ends up being that 0.364 times the cosine of 30 degrees. So that here is tangent 20 degrees times cosine of 30 degrees. Which I guess is what, is that root 3 over 2 cosine of 30? It's either a half or √3/2, right? I think it's, yeah, it's a longer one. So, and so we can do that, right? So we can multiply, let's see, I had a tab here with this number. Let's multiply it times cosine of 30 degrees. There you go. So 0.315. That makes sense, right? It should be less than the steepest rate of ascent. So now that is the actual rate of ascent. But what is the problem asking us for? Angle of ascent. So how do we get back to the angle? Arctan, right? We use the inverse tangent function to go back. We use tangent to go from the angle to the slope. We can use inverse tangent, arctangent to go from the slope back to the angle. So then the question asks what's, I guess again, these are things I'm just trying to glean as much as I can before I even get to the, and the question asks what is the angle of ascent of the branch trail? And the answer is now use arctan. We basically have, you know, we kind of have another side view again, but now it's like, now our side view is something that's a little bit less steep. I don't know if I made that less steep than the 20 degrees, but it's a little bit less. And this is the angle, but this is like 0.315 over 1, right? If you want to think of it that way. That's how you would write a slope as rise over run. You can always use 1 as your denominator. And so whatever this theta is, tan theta is about 0.315. So theta is arctan, inverse tangent, 5. So let's go back to the calculator. Can I do this? Can I write arctan of the whole thing? Oh, it like left the calculator, but it still gave me, oh, in degrees. 17.49 degrees. So theta, I kind of like the answer though, that the theta is inverse tangent of 20 times cosine of 30. But that's the actual, that's kind of the best. I mean, you could turn this into √3/2 if you want, but like, this is kind of the expression, the exact expression for the answer. But what is it? 17.5 degrees, basically. And again, that should make sense that it should be less steep, right, than the steepest. Cool. Okay. I sort of feel like I took the fun away from you by doing it, presenting it to you rather than letting you stew over it for a few hours. If you're upset with me, I apologize. But any questions about that? That was kind of a, put the question back on the screen one more time just to make sure. Yeah, so it's interesting, right? The two angles mean different things. One angle is like this kind of angle. The 20 degrees is this sort of angle, but the 30 degrees is this sort of angle. Okay, all right. Fun. Next time you're hiking, you come across a branch trail, bust out your protractors that you carry with you at all times, right? Yeah. Okay. And I don't know how you figure out the angle of ascent. I don't know. How did you figure out the angle of ascent to a trail that you were on? You'd have to figure out horizontal somehow. Oh yeah, leveler with a little bubble thing. Figure out what level is, and then some, I don't know. Okay. Anyways, all right. Cool. Okay, we've got like 20 minutes left. So let's take a breath. I think that's all I'm going to say about derivatives and directional derivatives. I will say, maybe just as the last thing, like directional derivative in 3D, like if you have a function of 3 variables, the directional derivative is still, there is a direction you would go to increase. Again, maybe it's something like you think of like a temperature, like you're measuring the temperature at every point in this room or something, and there's some heat source over there or something. So maybe the direction, maybe the gradient to direction is like towards the heat source. That would be the direction of greatest increase. It's now a 3D vector, not a 2D. Remember, for functions of 2 variables, the gradient's always a compass. It's always telling you which way to go to. It's almost like you have this special compass. You're walking around on a surface, you have the special compass that like tells you which way to go up the surface the fastest. But this is, so you would have like, so for the gradient would be like, yeah, towards the heat source. And if you want to know how the heat is changing, if you go off at some angle, it's still either you have the vectors explicitly and you can dot product the 2 vectors together, or you just know the angle and you can just magnitude of the gradient times the cosine of the angle. So that still works in 3D. You just have a lot more directions you can go. I don't know, it's all infinite. 2D, it's infinite number of directions. 3D, it's more infinite. There's actually this math of like, this is totally random, but math of random walks. Like if you, sorry, it's a little, the 2D versus 3D thing just made me think of this. Like, and you can even do there's 1D version of this. There's a whole theory of math called random walks, which is like, you put someone at 0, you give them a 50-50 chance of going left or right. At each step, you kind of flip a coin and you go one, if it's heads, you go one to the right, tells you one to the left. And you go back and you go off and you sort of trace, you sort of see how far, and there's like, after n steps, you can prove that it's on average your route in away from the origin. You can prove that you would revisit the origin infinitely often. In 2D, you can do a 2D random walk where you kind of walk on a grid instead, and now you need like a 4-sided, like a tetrahedron or something, dice to tell you to go left, right, up, or down. And if you do this, you can random walk on this, and you can also prove that you revisit the origin infinitely often on average. But if you go to a 3D random walk, where you can go up, down, left, right, or backwards and forwards, it turns out that you can get lost forever and not revisit the origin infinitely many times. So like somehow a random walk, birds on a random walk it's sad. You like lose your way. Because it's all, something's called like the drunkard's walk or something, where it's like you have a drunk person who's gonna randomly take a step left or right. on a 1-dimensional line, they'll find their way home. On a 2-dimensional grid, they'll find their way home. But drunk birds might be lost forever. Look what you learned today in class. Not exciting? Okay. Today I learned drunk birds might be lost forever. It's worth that Bowdoin tuition money. Okay. So yeah, so there's a lot of, it's almost like more infinite when you have 3D. There's more large, well, it's actually this, okay, I'm not gonna go. It's the same infinity, it turns out, but it's a larger infinity in some sense of directions that you have to go. Take Math 2020 if you want to learn about different types of infinity. Countable infinite, uncountably infinite. It's fun stuff. Okay, now let's talk about the chain rule for a few minutes. Well, last 15 minutes of class. So I don't think I need the screen for that. So I might just have it go up out of the way, so I can use the whole board. Okay. Let's talk about the multivariable chain rule. Let's introduce it. Then we'll have to pause our brains for a week until we come back next Wednesday. Let me at least introduce the concept. So let's recall the single variable chain rule, right? If y is, here's a different type of fu, f of u, and u is g of x. Let's just think, for example, let's just say like y is natural log of x squared plus 1. That's a nice chain rule example. So you could let u you know, the derivative dy dx, remember it's the derivative of the outside times derivative of the inside. So it's 1 over x squared plus 1 times the derivative of the inside, which is 2x. But we could write that if we write that as, if we call this x squared plus 1, if we call this intermediate variable u, almost like you do when you do substitutions and integrals and stuff, then we have y is ln of u is x squared plus 1, and dy dx is actually dy du times du dx. So the derivative of natural log is 1 over, right? So that's 1 over u times 2x. And that's exactly what we got here, just plugging back in for u, right? Remember, that's how it works. You could write this as f prime of u times g prime of x if you'd like also, right? This is f of u, and this is g of x. So it's really like, I guess this is g of f of x. No, I actually did have it right. It's f of g of x, right? The way I set it up. Prime. Got the right number of parentheses? No. Does this all sound familiar? Okay, but it's this thing where you multiply derivatives, right? And another way to sort of look at this is to say, let's present this as a hierarchy of variables. Y is a function of u is a function of x, right? So this is like a hierarchy of dependencies. And if you think about it, you could think sort of, okay, well, here is my dy dx is here, but I also have dy du and du dx. Right, my rate of change, because these are rates of change. This is the rate of change of y with respect to x. This is the rate of change of y with respect to u. This is the rate of u with respect to x. And that this is the product of these two, right? dy dx is dy du times du dx. And this kind of explains why we use this fractional notation, the Leibniz notation, because it's sort of like we can think of the du's canceling, right? Okay, so that's kind of how the chain rule works in one variable. What if we had something a little more complicated? What if we had like a multivariable dependency? So multivariable version. So let's say, let's give an example again. Z is, actually I'm gonna do a 3 variable. So W is x squared y plus z, but x is u plus v, x is u plus v, y is u minus v, and z is u times v. I guess I've actually switched the hierarchy of u's and v's a little bit here. I mean, I put the x's in the middle, I guess. But it should be okay. Hopefully you can handle that. So now we have W as a function of x, y, and z. Right, here's the hierarchy. And then x, y, and z are both functions of u and v. So we have something like this. It's kind of a crazier diagram, right? But you can imagine something like this. And what if I wanted to know the rate of change, say, of W with respect to U? there's sort of a couple different ways to go about this. You could just plug all these in and write W in terms of U and V, right? I could write U plus V quantity squared times U minus V plus UV. Yeah, so like what is, now notice this is gonna be a scripty because it's a partial, because W depends on, well, at the bottom layer, it depends on U and V. So it would be the partial derivative of U, of W with respect to U. Okay, let's think about this. Well, we have differential type stuff that we've thought about before. So that's going to be useful. Let me see if we can write this down. Kind of carefully. So let's see. So basically, if we change U a little bit, how do we change, what's the corresponding change in W, right? So I'll say let me just say method one is what I said before, where you could just plug in so like W here would be U plus V quantity squared times U minus V plus UV, and then compute the partial, compute this directly. But depending on how complicated this is, this could just be kind of nasty in terms of algebra and stuff. Like if that had been U plus V to the, if that had been X to the 10th power instead of X squared, this would be very unpleasant to expand out U plus V to the 10th, right? So method two is, let's think about this. Let's think a little more conceptually. Given a delta U, what is the corresponding delta W? Okay. Well, let's see. We have W in terms of X, Y, and Z, right? And so we know that we can use these kind of differential type formulas that we did in like section 14.3. We know that delta W is approximately the following, right? It's dW dx delta x plus dW dy delta y plus dW dz delta z. Remember, if you wanted to compute the change, this comes from that, like, we looked really carefully at the two-dimensional version of this picture with just x and y, right? And we saw that like partial x times delta x plus partial y times delta y was basically the change in the function. That sound familiar? Okay, so we know this. We know this. This is sort of like the differential or tangent plane or whatever idea. Okay, now here's what we could do. We could divide through by delta U. Divide both sides by delta U. Because that's what the rate of change of W with respect to U is. It's basically like the change in W over the change in U, but let those get smaller and smaller. Like let the change in U get smaller and smaller, right? So divide both sides by delta U. So we get the change in W over the change in U is approximately, well, I can now remember like X, Y, and Z are all functions of U and V. So I'm actually going to divide the delta U underneath the delta X, the delta Y, and the delta Z. So dW dx times delta X over delta U plus dW dy times delta Y over delta U plus dW dz times delta Z over delta U. I should say this is exactly the same thing that we do in single variable calculus where we say like the change in y is approximately dy dx times the change in x, right? This is like rise over run. This is rise and this is run and this is slope. So rise is slope times run, right? So it's the same idea. It's a little bit off screen for that, but sorry. Okay, so this starts to look crazy, but because there's a lot of variables going on here, but now like the whole point is that in the limit as delta u goes to 0, these actually become derivatives like partial w over partial u. So now you let delta u go to 0, and these become, you know, it's that whole derivative thing where you're really computing 0 over 0 in strange ways. But if you let delta u go to 0, these become partials, and this approximation becomes an equality. So you get dw du is dw dx dx du plus dw dy dy du plus dw dz dz du. And this looks like some crazy nonsense. Now you can't do the cancellation thing, because if you cancel the dx, the del x's, del y's, del z's, you get dw du equals dw du plus dw du plus dw du. That's not good. But how do we like think about this? So here's how I think about this. Now this is the multivariable chain rule for this expression, right? Like this is what the multivariable chain rule says. It's a little abstract. We can do it, but we could do it using like, you know, we could plug it, we could sort of calculate all these things, but let me just, because we're gonna run out of time in a minute, let me just draw this hierarchy again. And let me leave out, let's leave out V for now, just for the clarity of the picture. Right? What we want is we want the whole thing, the change in W with respect to U. But notice here we could think about the change in W with respect to X, change in X with respect to U. It's almost like there's 3 paths from W to U. You see, you can go through X, you can go through Y, you can go through Z. And I can think about putting dW dy here, dy du here, dw dz here, dz du here. And notice what this says. This says the change, the total change is this times this. So it's like following this path, plus this times this following this path, plus this times this following this path. So it's almost like we sum over paths from W. We multiply along paths. This is the way I conceptualize this. We multiply along paths, then sum over paths. And that gives us the formula that's up here. So you have to sort of think, because this looks horrible, but it's kind of like you're just passing through each intermediate variable. There's 3 intermediate variables now, X, Y, and Z. So I have to pass through each of them. And it's like and each of these is almost like a single variable chain rule where you're just multiplying the derivatives. Okay, sorry, we're out of time, so I don't have time to do an example, but that's kind of the concept. I'll revisit this next Wednesday, get us all back on the same page, but I just want to introduce it today. So, all right, fun. Guys, I won't see you Friday, I'm very sad. I won't see you Monday, I'm still very sad. I will see you in 167 hours. Aren't there 168 hours in a week? Maybe.